Alright, so this is the last video. Once again, I'm just going to summarize all the results that we have used in this chapter, which is basically just one particular topic, Monte Carlo, evaluating integrals using Monte Carlo integration. So in summary, if fx is a PDF, that is a probability density function with support set A, that is fx is greater than or equal to 0 for all x belonging to A, and the integral fx dx is 1 over the support set, then to estimate theta, which is an integral gx fx dx. Now you might be thinking, what is this fx? You probably haven't seen it that often. Remember, we were generating uniform 0, 1, and in those situations this was 1. Or we were using uniform A to B, and in those situations this was 1 over B minus A. But this is like a general version. So your theta that you want to evaluate is over the support set of fx gx dx. What you do is generate a random sample. So the first step is generate a random sample x1, x2, xn IID from fx. So we had 3 examples. Once the fx was uniform 0, 1, in another example our fx was A to B, in another example our fx was standard normal CDF. And second step, compute sample mean theta hat for that function, for the function g. So 1 over n sum of gxi. So that's your theta hat. So this is your theta. Oops. That's your theta, and this is your corresponding theta hat. Now, some properties of this theta. So remember the 2 key theorems that we use in Monte Carlo evaluation of Monte Carlo integration are central limit theorem and strong law of large numbers. So strong law of large numbers is used to get theta hat. So theta is gx fx dx over A. Theta hat is 1 over n sum gxi. I goes from 1 to n. This is true because theta hat converges to theta in probability as n goes to infinity by strong law of large numbers. And by CLT, that is central limit theorem, theta hat minus expected value of theta hat divided by standard error of theta hat goes to the distribution of this thing approaches normal. The distribution goes to normal as n is sufficiently large, where standard error of theta hat is equal to 1 over n sum gxi minus gx bar square. Also, we can show that theta hat is we can evaluate the expected value of theta hat. Let's do that. So let's add one more slide here. Expected value of theta hat is equal to expected value of 1 over n sum gxi, right? I goes from 1 to n, which can be written as, because they are independent and identical, so it's 1 over n sum I 1 to n expected value of g xi, since xi's are IID, and 1 over n sum I 1 to n. Now expected value of gx is gx fx dx, right? So then this is the integral gx fx dx. Since this is PDF of fx, so for example, if we were to, let me just like maybe on an easier note, so if we were, think of it as if we were to generate our x from uniform A to B, then this A, the support set would be A to B, and this would become 1 over n 1 to n A to B gx, and fx would become 1 over b minus a dx. F of x would be 1 over b minus a, and in that case it would become from 1 to n gx dx. And oh yeah, I am forgetting the b minus a. If I use this, then this would be not 1 over n but b minus a times of this. So I would have a b minus a here, and then there is a b minus a. So this cancels. So this becomes, and the summation is just n over n gx dx, which is, so it's just one example of how your expected value of theta hat is actually theta. So in this case theta would be unbiased. So if your x was coming from uniform AB, you could show that the expected value of theta hat is coming from is theta, which is unbiased. So I'll just stop here. If you have any questions, feel free to post them on discussion board.